Hello and welcome. Tonight we drift through questions that keep even the most patient scientists awake. Begin with the invisible weight that holds galaxies together. Astronomers can weigh a spiral galaxy by how fast its outer stars orbit. Those stars circle as if a vast halo of unseen mass is pulling them in a quiet grip. This hidden mass is called dark matter. It does not shine or absorb or scatter ordinary light. It seems not to be made of the familiar particles inside atoms. Sensitive underground experiments wait for a whisper of contact with a dark matter particle, and the universe continues to say not yet. The cosmos, it seems, keeps a secret account book whose entries do not appear in ordinary currency. There is a second enigma. The expansion of the universe is not merely continuing, it is gently accelerating, as if space itself has a faint pressure that pushes galaxies apart. This effect is called dark energy. Imagine an elastic sheet that, instead of relaxing, grows ever so slightly more taut each moment. The pressure is weak, yet over billions of years it becomes the rhythm of large-scale structure. We can write equations that describe the push, but the substance of the push remains unnamed. Is it the energy of the vacuum itself, or an evolving field quietly bathing all of space? The sky does not say. It only keeps expanding. If we look back in time, we arrive at a very early, very hot state that we call the Big Bang. But what was before the beginning? The familiar word before may not apply because time appears to be woven into the fabric that began. Some ideas suggest a bounce from a prior contraction. Others imagine a timeless quantum fog where the seed of our universe tunneled into being. Why does the arrow of time point from past to future? Perhaps it is because the early cosmos had remarkably low disorder and has been relaxing ever since, like a wound spring unwinding for billions of years. Yet why the spring was wound in the first place lies behind a closed door. There is the puzzle of matter and its mirror. When energy turns into particles, it should create equal amounts of matter and antimatter. Put the mirror twins together and they vanish in a burst of light. The young universe ought to have erased itself, and yet here we are, made of matter. Subtle experiments reveal tiny imbalances in the decays of certain particles, hints that the laws of physics slightly prefer matter over antimatter. The preference is too small to explain the whole cosmos. Somewhere, perhaps in forces we have not yet seen, a stronger bias was written into the earliest moments. Another idea says the universe, shortly after its birth, experienced a brief and stupendous growth spurt called inflation. In less than a heartbeat, space may have expanded by an unimaginable factor, smoothing and flattening the cosmos and planting the faint ripples that later grew into galaxies. The mathematics works with grace, but what lit that flash and what turned it off? Astronomers search the sky for the curling fingerprint that such an event would have left in ancient light. The fingerprint remains elusive, and the question lingers like a soft echo. At very small scales, particles behave like waves and probabilities rule. At large scales, gravity curves space and time, guiding planets and light itself. To fully understand the universe, we must combine these two grand descriptions into a single quiet theory of quantum gravity. Many paths are being explored. None has yet shown the undeniable landmark that says you have arrived. We listen for a harmony that blends the music of the very small and the very heavy. And for now, we hear two beautiful melodies playing side by side. Black holes add their own whisper. According to the rules of quantum physics, they should slowly evaporate, letting a faint mist of radiation seep away over unimaginable periods. If so, what happens to the information about what fell in? Is it lost, smeared on the event horizon, or released in some subtle code? The universe allows no easy destruction of information, yet a black hole seems to hide a library and then dissolve the walls. The resolution to this paradox is still being written letter by letter in equations that test the edge of our understanding. To reach quantum gravity, some physicists imagine that space has tiny vibrating strings, or that geometry itself is built from loops knitted together at the smallest scale. Strings can explain a zoo of particles, as different notes on a single instrument. Loops give atoms of volume to space itself. Both visions are bold, yet the world has not yielded a clean experimental signpost. The most careful measurements keep turning up the same calm result. Space looks smooth, and particles look point-like. The hints are delicate, and the search goes on. Above the atmosphere, there are messengers that arrive with energies far beyond what our accelerators can produce. These are the most extreme cosmic rays. They are like pebbles flung from catapults we have not yet seen. Are they hurled by magnetized winds around black holes, or born in the shock fronts of colliding galaxies? As they cross the universe, they are bent by magnetic fields and lose energy to the sea of ancient light, so tracing them back to a source is like following ripples across a crowded pond. Each rare detection is a small note, and the melody has not yet been decoded. We now know that the sky occasionally releases a millisecond shout at radio wavelengths. These fast radio bursts are more powerful than the combined radio output of entire galaxies during their brief flare. Some repeat, some do not. Some dwell in the hearts of dwarf galaxies, others in the suburbs of spirals. They may be the cries of highly magnetized neutron stars, or the snap of cosmic strings, if such strings exist. For now, they are lightning at a distance, fascinating and brief. Another thought whispers through modern cosmology. If the constants of nature were very slightly different, stars might not burn long enough to forge the elements of life, or atoms might not hold together. The dials appear finely set. Perhaps there is a larger room of many universes where the dials vary, and we naturally find ourselves in a life-friendly corner. Or perhaps there is a deeper reason that fixes the settings. The question touches philosophy and physics in equal measure and invites humility more than certainty. Time itself is a riddle. We experience a now that slides forward, yet the laws of physics treat past and future with a near-perfect symmetry. Why do we remember yesterday and not tomorrow? One line of thought ties the arrow of time to the growth of disorder, which seems to climb as the universe expands. Another connects it to the way quantum systems become entangled with their surroundings, shedding the crispness of pure states. We live within time, and so we cannot step outside to look at it directly, which makes the mystery gentler and also deeper. Neutrinos add a playful note. They flood the cosmos in uncountable numbers, pass through planets as if through fog, and only rarely tap the shoulder of ordinary matter. For decades they were thought to be massless. Now we know they change their flavor as they travel, which requires a non-zero mass. How heavy are they exactly? Do neutrinos and antineutrinos behave with a tiny difference that helps explain why matter won the early cosmic contest? The answers are being pursued in long tunnels, deep mines, and polar ice. There may even be a hidden cousin called a sterile neutrino that interacts only through gravity, a ghost of a ghost. Hints have fluttered in certain experiments, then faded. If such a particle exists, it could affect how galaxies grow and perhaps be part of the dark matter story. For now, it remains in the waiting room. A maybe in a world that prefers yes or no. Another quiet worry concerns the vacuum itself. Our current theory of particle physics suggests that the fabric of space may rest in a not quite absolutely stable state, like a ball in a shallow dent that could, in principle, tunnel to a deeper dent. If that ever happened, it would rewrite the laws of physics at the speed of light. The probability appears to be unimaginably small over times much longer than the age of the universe, and yet the possibility exists in our equations like a faint note you can hear only at midnight. Watch a black hole and you may see narrow jets of material shooting out from the poles at nearly the speed of light. They pierce the bright surroundings and can extend for thousands of light years, staying collimated like cosmic needles. How do they tap energy from a rotating hole? How do magnetic fields thread a place where space itself is twisted? Computer simulations have grown exquisite, yet the complete engine room remains partly veiled in hot plasma and gravity. Some theories suggest that space has more dimensions than the three we walk through. The extra directions could be curled up so tightly that we cannot step into them. If they are real, gravity might leak into those directions, or new particles might wink into existence at high energies. Experiments have looked for these signs and so far have found silence. It may be that the extra dimensions are there and very small, or that nature chose another road entirely. Even the magnetic fields of galaxies ask for an origin story. Stars, gas, and dust swim within wide loops of magnetism that can guide charged particles and light up radio waves. A seed field could have been amplified by the slow turning of galactic disks, much like a dynamo. But where did the seed come from? From the early universe itself, or from newborn stars blowing bubbles into space? The answer requires measurements as delicate as spider silk stretched across light years. Between galaxies lies a nearly invisible web. In that web hide the missing ordinary particles from the first billion years, warm and thin, difficult to see. Astronomers have begun to trace them by how they absorb light from faraway quasars or glow faintly in X-rays when struck by restless electrons. The tally is improving, but the census still feels like a quiet count in a dim room. At the grandest scales, the universe resembles a foam of filaments and voids. Gravity draws matter along highways into clusters, leaving wide regions relatively empty. Why does this network have just this pattern? The mathematics of growth from small initial ripples fits beautifully, yet it relies on the character of dark matter and dark energy, which we do not yet fully know. It is as if we can predict the shape of a tree, but not the sap that sustains it. Turn now from the biggest questions to nearby puzzles that touch the moon and our neighboring worlds. Our moon has a composition so similar to Earth that many scientists favor a giant impact early in planet formation. where a Mars-sized body struck the young Earth and debris gathered into a satellite. Yet the isotopic match is uncannily close, and the physics of the impact still leaves room for debate. The Moon carries a quiet history book, and we are still learning the language. Mars once held rivers that carved deltas and lakes that endured for long stretches. Its sky was thicker and warmer. Where did the water go? Some is locked in polar caps and hidden ice, much likely escaped into space as the planet lost its global magnetic shield and the solar wind stripped the upper atmosphere away. The exact timeline and balance are being pieced together from rover rocks and orbiters that measure whispers of vapor. Saturn keeps a curiosity at its north pole, a persistent hexagon in the clouds. It is a jet stream that circles and somehow locks into a six-sided shape. Laboratory fluids can make similar polygons under rotation. But the details of the planet's size version still invite study. The giant ringed world holds its geometric secret with a slow smile. Jupiter hammers the definition of weather. Its lightning is deeper and may be powered by water clouds mingled with ammonia. Its storms dance around a planet that rotates in less than half an Earth day, where the Coriolis effect is strong and the scale is continental. The physics that rules a Jovian thunderhead is familiar yet profoundly amplified, and there is more to learn with each new orbit of a visiting probe. Beyond the giants, several small moons are likely to have oceans beneath ice. Europa and Enceladus vent plumes that hint at salty water in the dark, warmed by tidal flexing. These seas may have energy and chemistry that could support life, perhaps microbes, perhaps something more complex that moves slowly in a lightless world. We do not know. Future missions will taste the plumes and listen for faint organic songs. Titan, a moon larger than the planet Mercury, hosts rivers and lakes made not of water but of liquid methane and ethane. There is a methane cycle akin to the water cycle on Earth, with evaporation, clouds, and rain, all at temperatures far below freezing. The chemistry is rich and strange. Sand dunes are made of hydrocarbons blown by an alien wind. We can describe the flows, and yet the full story of how this world keeps its balance is still unfolding. The rings of Saturn may be young, bright with ice that has not been dulled by cosmic dust for very long, or they may be ancient, a remnant of shattered moons. Measurements of their mass, their erosion, and their slow infall toward the planet lead to different ages. The rings could be a passing flourish in the long life of the system or an enduring archive. Both possibilities are beautiful, and the evidence remains gently ambiguous. Comets carry frozen gases and dust from the deep freezer of the solar system. Their dark crusts and fluffy interiors preserve clues to the early solar nebula, but each visit to the inner sun alters them, resculpting surfaces and releasing jets that change a comet's spin. We land on them, sample them, and still argue about where exactly in the primeval disk their cores first formed. They are both archives and artists, rewriting their own pages. Mercury hides a giant iron core that fills much of the planet's interior. How did a world end up so metal-rich? Perhaps a violent collision stripped away the lighter rock. Perhaps the early sun's heat baked off the silicates. Perhaps magnetic or chemical sorting in the solar nebula did the work before the planet was even fully formed. The small world close to the sun offers clues and then turns away. Venus is Earth's sister in size, yet its surface is an oven and its clouds are laced with sulfuric acid. The greenhouse blanket is so thick that rocks glow with heat. Did oceans ever exist there? Are volcanoes still quietly breathing under the clouds? Radar reveals mountains and plains, and slow changes hint at activity. But the story of how a world so similar in bulk became so different in spirit remains a cautionary tale we do not fully understand. As you settle deeper into the night, let the unanswered questions work like soft waves. Each mystery is an invitation, not a wall. Science does not fear the unknown. It tends the unknown, studies its edges, and waits with patience. The universe is not silent out of indifference. It is silent because we are still learning its language. And in that learning there is a calm, steady joy. Here we drift onward through the gallery of unanswered questions, letting the mind move as gently as a tide across sand. The air is quiet, the room is still, and curiosity is free to wander. Some rocks speak in pulses of magnetism. They keep memories of ancient fields that once wrapped the planet, yet there are stones that suggest the field flickered and faltered at strange moments that do not line up with any known trigger. Why some volcanic flows lock in directions that hint at temporary lurches, or why certain sequences show a near standstill of the geodynamo remains unsettled. We can model molten iron swirling in the core, and we can measure faint murmurs at observatories, but we cannot yet read the heart well enough to say why the planetary compass sometimes stutters. There are deserts where the wind draws neat furrows called yardangs and sculpts ripples with a regular rhythm. Then there are rare places where boulders creep as if alive, leaving tracks across dry lake beds. Ice collars form under stones, winds push. Thin films of water reduce friction, and the sun works like a slow engine. Yet the full choreography is still disputed. The tracks are signatures of many small forces that add up to motion. And because the steps are so slow, we keep discovering new ways that rock can be persuaded to wander. Out on the open sea, mariners still whisper about solitary walls of water that rise from a placid surface with no warning. Instruments have confirmed them, photographs have caught them, and platforms have felt their weight. These rogue waves are not mere legends, yet the way a random field of swells will suddenly focus its energy into a single crest is not fully pinned down. Non-linear mathematics points to packets that steal energy from neighbors, currents that tilt the stage, and winds that pump a resonance. But predicting the exact place and hour is far beyond our reach. The ocean keeps that card close. The planet as a whole has worn a cloak of ice more than once. There are scars on the continents and isotopic clues in ancient sediments that speak of a deep freeze when ice may have reached nearly to the equator. How such a world started and how it thawed without the help of sunlight strong enough to undo the white mirror is still a story with missing pages. Volcanic carbon dioxide building up beneath a blanket of snow, the darkness of dust dropped on ice, and slow shifts of continents might together have turned the key. But the order of events and their pacing are still debated. The line between a glistening marble and a frozen mirror is thinner than it seems. When we ask where our water was born, the answers scatter like rain on pavement. Some droplets likely fell from the sky of early space as icy comets and carbon-rich asteroids, their hydrogen fingerprints recorded in the ratio of heavy to light atoms. Some may have been forged within the planet, bound in minerals deep in the mantle and exhaled through a billion ancient breaths of volcanoes. Pinning down the exact mixture is difficult because the fingerprints can be blurred by time. Each basaltic glass shard, each meteorite pebble, each vein of crystal holds part of the riddle. Under the sea, the floor can slump like a slow sigh. Whole slopes of sediment may give way, sending vast clouds of grains rolling downhill for many kilometers. We know these underwater landslides can awaken tsunamis. And we can see their frozen shapes in seafloor maps, but we rarely catch them in the act. Was it a distant earthquake? Gas bubbles escaping from pore spaces, or the quiet accumulation of mud until a threshold gave way. The triggers are layered like blankets, and because eyes are scarce in the deep, much of the story happens in darkness. The great switching between warm and cool waters in the Pacific, the pulses called El Niño and La Niña, remains a puzzle that we can describe and even partly predict without fully explaining. Winds slacken, the thermocline tilts, and warm pools slide across the basin, changing rain and drought for faraway lands. But the reason the system tips in one particular year rather than the next, and why cycles sometimes cluster, is still being explored. The ocean is a basin full of sloshing notes, and some of its chords are only now being heard. The monsoon is another grand example of an engine that knows more than we do. Every year, continents heat and cool, pressure fields shift, and walls of cloud advance with ceremony. Yet the strength and timing of each season, the sudden breaks and bursts, can still surprise even the best models. Mountain ranges guide the wind like organ pipes, sea surface warmth feeds it, and soil moisture remembers last month in a way that can tilt tomorrow. The levers are many, and the orchestra is global. In North Africa, there were eras when what we call the desert put on a green coat, lakes filled, hippos swam, and people painted boats on rock. After thousands of years, the rains withdrew, leaving dunes and stone. Changes in the slow wobble of the planet, the position of the tropical rain belt, and subtle feedbacks with vegetation all played roles, but the exact sequence of how grass invited more rain, which invited more grass, is still being worked out. The Sahara holds its own diary, but we have only skimmed the margins. We have a neat story for the end of the dinosaurs that points to a large impact and a winter of dust, yet the timing of volcanic outpourings, the state of ecosystems before the rock fell, and the way the oceans responded in different regions add layers of complexity. The Great Extinction reads like a symphony with a sudden drum strike, but quieter motifs were already playing. How the notes combined to make an exit so final is an ongoing debate that turns on tiny fossils and rare metals in clay. Before some earthquakes, observers describe strange lights dancing, veins of luminous mist, or the glow of air along a fault. The reports go back centuries and appear on every continent. Some ideas point to electric charges generated by strained rock, others to piezoelectric sparks or coronas at the tips of stones. Because these displays are rare, short, and unpredictable, gathering solid evidence is hard. If the lights are real, they are one more way the Earth whispers before it shouts. Beneath Antarctica, radar instruments have traced ghostly paths of rivers and the outlines of lakes sealed beneath ice for a very long time. We have learned to drill and sample with care, and we have tasted waters that never saw sunlight. The puzzle lies in how these networks start and persist, how pressure melting, geothermal warmth, and friction from sliding ice play together to keep rivers awake in a place that feels like sleep. The hydrology of a continent under glass is a new frontier. The long dance of carbon between rock, water, air, and life is another story with many authors and a plot we do not fully grasp. Microbes precipitate minerals, mountains rise and grind down, plankton build shells and rain to the abyss. Volcanoes exhale, and forests breathe. The slow pump that regulates carbon on million-year scales controls the climate's long mood, yet the strengths of the valves and the tempo of the gears are still measured with wide margins. The machine works, that much we know, but its blueprint is tattered. There are nights when the sea does not sparkle in scattered specks, but glows like milk poured from horizon to horizon. Sailors told these tales, and satellites have begun to find the luminous blankets. Perhaps a rare arrangement of bacteria living on algae talk to one another and switch on as a crowd. Perhaps the glow is tied to slick layers at the surface. Perhaps both are true. Because these events cover wide spaces and can last for hours, they are difficult to study up close. For now, they remain gentle sea poems written in light. Life itself is threaded through with mysteries that soften the mind. Inside the genome are sections of repeating letters that seem to expand and contract across generations for reasons not fully known. Some repeats trigger disease when they grow too long, others appear to be harmless passengers. The machinery that copies DNA sometimes slips on these runs like a foot on ice, yet why certain loci are so prone to this dance is not clear. The script is legible, but punctuation still moves. Cells that live without oxygen but leave traces of oxygen chemistry in ancient rocks complicate the story of the early Earth. Were there tiny oases where microbes split water long before the atmosphere turned blue? Did lightning and ultraviolet light make oxidants that confused the record? The rocks carry messages, but the ink has bled, and interpreting it demands patience and humility. In some animals, whole bodies can be nearly frozen and then revived, while others resist radiation in ways that defy our expectations. The biochemical tricks that protect proteins and membranes, the sugars that glass the interior of cells, and the repair crews that stitch broken strands of DNA are only partly catalogued. We know that life can hunker down far more stubbornly than we once thought. We do not yet know the full recipe for such resilience. Brains offer a different set of questions that are both intimate and vast. Why do we dream the way we do? The stages of sleep have been mapped with careful wires, and the rhythms of slow waves and rapid eyes are now familiar to science. Yet the role of bizarre narratives filled with impossible scenes is not settled. Memory consolidation, emotional bookkeeping, creativity, and random housekeeping all have their advocates. Perhaps the mind uses the night to walk the corridors of itself, and perhaps it leaves the lights on so it will not stumble. Music can move us to tears with a sequence of vibrations that has no clear survival value. Why certain intervals feel resolved while others feel tense. Why a cadence hints at home, and why the human brain seems tuned to meter and beat is a story that spans physics, culture, and evolution. Infants sway to rhythm before they can speak. Whales sing across oceans, yet the bridge from pattern recognition to awe is not yet fully drawn. There are people who taste shapes or see colors in numbers, a condition called synesthesia that blurs the borders of perception. It clusters in families and appears more often in artists and mathematicians, but a satisfying neural map that explains the variety of pairings remains elusive. Perhaps the developing brain prunes less aggressively, leaving crosstalk between areas, or perhaps attention circuits bind disparate signals more easily in some minds. The experience is real, but the wiring diagram is sketchy. Placebo effects are another quiet marvel. A sugar pill cannot block an infection, yet belief can change pain, nausea, and even some measurable biomarkers. The brain's pharmacies open when rituals and expectations are in place, releasing natural opioids and neurotransmitters, but the full rules for when and how these internal dispensaries act, how long they can sustain relief, and how to harness them ethically are still being written. The mind is not merely a passenger, it has a hand on the tiller. Memory, too, is stranger than we think. Some people remember every day of their lives with a clarity that can be burdensome, while others forget the beach they walked only last week. We know of hippocampal circuits and cortical archives, but we do not fully understand why certain experiences stick like burrs while others wash away. Emotion tightens the knot, repetition strengthens the weave, sleep seems to set the die, yet surprises remain. Language blooms in children with a speed that takes the breath. In a few short years, they infer grammar from a stream of imperfect sentences and invent words for ideas they have never heard named. Which parts of the brain carry an inborn scaffolding and which parts grow purely from exposure is still debated. The seed and the soil both matter, but the exact mix is not known. There are animals that navigate by sensing the Earth's magnetic field. Migratory birds correct their headings under cloud cover. Sea turtles return to natal beaches years after hatching, and tiny insects take routes that make sense only if magnetism whispers to them. The sensors may be quantum reactions in light-sensitive proteins or iron crystals in tissues. They may even be both. The magnet sense is real. Its biology remains a riddle in progress. In the micro world, certain bacteria build perfect crystals of iron, align them in chains, and use them like compass needles. How such biomineral factories control nucleation and growth at room temperature in salty water is a lesson materials science would love to master. The blueprint exists in genes, but the steps of the assembly line are still being discovered. Plants talk in vapors and in underground cables of fungi. Forests exchange signals about pests and drought and can reroute resources through shared networks. How much of this is cooperation? How much is defaults of chemistry? And how much is a byproduct of ancient bargains is debated. The story is poetic, but it is also practical, and we are just beginning to translate. Viruses are pieces of code wrapped in protein, yet they can build filigree shells of near mathematical perfection. Some switch between shapes like origami that folds and unfolds on command, predicting the exact form a given sequence will take. In detail and at speed is a challenge that modern algorithms are only beginning to meet. Nature's nanotechnology keeps its head start. We also face enigmas in the realm of timekeeping. The body uses light to align with day and night, yet tidal animals keep their own many-hour clocks keyed to the sea. Some genes act as the gears, but the way multiple rhythms coexist without chaos is still being charted. Life is a choir that sings in overlapping tempos. The score is not yet fully annotated. The placebo's mirror image, the nocebo effect, can worsen symptoms when expectation is dark, explaining how stories we tell ourselves exert such power over physiology is as important as any clinical lesson. The ethics of harnessing comfort without deception is an open conversation that blends neuroscience with philosophy. Certain cancers regress on their own. Inflammation turns and walks away as if a hidden switch restored order. We know of immune surveillance and checkpoints. We design therapies that awaken the guards, yet the spontaneous turnarounds still surprise. Understanding them fully could change everything. In technology and mathematics, there are also soft shadows. We can train neural networks to label images and compose music, yet we often cannot say precisely why a particular layer chose a particular feature. Interpretability is improving, but the opacity of decision pathways remains a challenge. We build mirrors that learn and then struggle to see ourselves in the reflection. Prime numbers seem to arrive at random, yet on the scale of many thousands they follow precise statistics, leaving gaps that echo probability. The twin primes, numbers that differ by 2, appear to continue forever, but a final proof still glimmers just out of reach. Mathematics has many settled lands and many open seas. Consciousness itself sits at the center of the web. We can map correlations between patterns of neural activity and reports of awareness, and we can disrupt networks to change what people feel. But a satisfying explanation for why a certain arrangement of electrical whispers is accompanied by the glow of experience is not in hand. It may be that explanation will require new words, or it may be that careful work with existing tools will gradually remove the mystery. For now, it keeps us humble. Even the simple question of why humans sleep as long as we do when sleep seems to make a creature so vulnerable is still under discussion. Glymphatic cleansing of metabolites, the cementing of memory, the pruning of synapses, and energy management all contribute. Yet the full balance sheet is not reconciled. Nature rarely pays such a high nightly cost without many benefits. We are still listing them. When you watch the breath move in and out, reflections like these settle into a steady hum. Not knowing is not a failure, it is an invitation. Science advances by turning questions into better questions, and mystery feeds that work the way rainfall feeds a spring. If the mind is ready for rest, let it drift on the knowledge that there is so much left to learn, and that the world will be waiting in the morning with both answers and new wonder. Here is the next calm stretch of the documentary, carrying on in the same gentle voice and style as before. It flows directly after the last section you received and continues the theme of enduring scientific mysteries, moving steadily from the living swarms of Earth to the oldest riddles of evolution and deep time. Life sometimes thinks with more than one body. When a cloud of midges hangs over a field at dusk, it appears to pulse like a single animal, a shimmer made of thousands of wings. The rules that turn many into one remain partly hidden. Biologists can write equations that nudge digital dots into spirals and waves, yet the real swarm always does a little more than the model. In a school of fish, each animal takes in the world as a ribbon of pressure and light along its flanks, aligning with a few neighbors, then revising the alignment again a heartbeat later. The dance survives gusts of water, hunger, and surprise. Somewhere inside those simple rules may live a form of memory, a capacity to keep shape without a brain, and that is not fully explained. Bees add a further layer of mystery. A scout returns from a meadow and shivers through a figure that looks like a tilted 8. This waggle points to food, yet it is not a fixed code. It bends with wind and hills, and with a whisper of scent that cannot be graphed easily on paper. How a colony fuses thousands of these messages into a single decision remains an open book. In some years, hives weaken and fail across continents. Pesticides, parasites, poor forage, stress from transport, and disease all play roles. Yet the full pattern of collapse, why it arrives in some valleys and not others, and why it rises and falls with no simple rhythm, is still being learned. Termite mounds breathe like lungs that do not rest. They hold stable temperatures through heat and cold, using only dirt, holes, and the daily sun. Engineers copy these towers to cool buildings without machines. But the plan is not as simple as chimney updrafts. There are changing vortices within the walls and pressure tides driven by distant gusts that we are only now tracing with dyes and gentle sensors. The blueprint is printed in the dirt itself, in the thickness of passages and the curve of galleries shaped by blind builders, guided by signals that are still being found. Birds cross oceans guided by a compass that sits in the eye and another that may live near the beak in tiny grains of iron. Quantum states, which seem so fragile in a laboratory, might persist long enough inside a protein in the retina to steer a robin by the angle of twilight. The physics is still debated kindly by chemists and biologists at conferences where slides flash in dark rooms. In the open air, a young bird leaves a nest it has never seen from above, and weeks later lands on an island it has never touched. The math of that leap remains to be finished. Eels slip into the black water of autumn rivers and do not return for years. They change shape in the open sea, become silver and lean, and glide toward a region we call the Sargasso. The exact cradle of their young has been only partly mapped. What these animals do in the deep nights of the ocean, how they choose partners, and why the pull of that far patch of water is so absolute are questions that have rested on the desks of naturalists for generations. A few tagged bodies have sketched hints, but the full map is still incomplete, as if the ocean had politely blurred the lines. Whales sing near mountain chains of stone that lie below the water. Their songs carry over distances that are hard to imagine, sometimes across whole basins, helped by sound channels that bend within layers of temperature. Why some pods strand together on gentle beaches remains imperfectly known. Storms, sonar, geomagnetic kinks, illness, panic, tight family ties that refuse to break, each can play a part, but the cause is not a single thread. The vulnerability of a mind that refuses to leave a sick relative may be, in part, what draws these giants to shore. Sharks and turtles find home beaches years after they were born. In their bodies, tiny crystals of iron have been found, and in their behavior a sensitivity to fields as weak as the one the Earth provides. Yet, the way this sense is wired to the map in the brain, the way changes in the field during storms and solar weather are discounted, remains to be shown. A turtle the size of a dinner plate leaves a beach and vanishes into blue, then returns as a wide shell as old as a small child, and walks with quiet certainty toward the dune grass. Somewhere in the long memory of the sea, a line has been kept for it. Corals tell time by the moon. In certain warm nights, thousands of colonies release clouds of eggs and sperm into still bays, a snow of life that drifts and meets. The exact clock sits not only in lunar light and tide, but also in molecules that tick within each polyp. Why certain nights are chosen with such fidelity, and why a whole reef can hold its breath and then exhale together, is not fully understood. These mass spawnings have allowed reefs to rebuild after storms for ages, yet their timing remains a soft secret. Plants speak without a voice. Through fungal threads, they trade sugars for mineral gifts, and they pass along chemical warnings that change leaf chemistry before the first bite is taken. Electrical pulses move from root to stem and back again at speeds slow enough to miss if one blinks too fast. What counts as memory in a plant, how long a warning is kept, whether an individual tree can be said to learn in a way that fits that deep word, is debated kindly. Forests can appear to adjust to drought by moving water along hidden unions among roots. The exact rules of that gift economy still wait for a fuller grammar. A slime mold spreads across a dish in a lab and finds the shortest path through a maze. It has no neurons, no mouth, no eye, yet it solves a small puzzle set by a graduate student who smiles in surprise. The mold lays down a network of tubes that thickens along productive roots and thins along poor ones. This mind without a brain drifts toward efficiency. Where is the calculation performed? How are costs and benefits felt in a body that cannot count? Why do these networks keep memory after the food is gone? These are open doors. The origin of flowering plants, the old, abominable mystery of a 19th century naturalist, still holds some of its shadows. Fossils appear as if a curtain had been lifted in the middle stretch of ancient time, and suddenly forests have blossoms and seeds tucked into protective coats. Genetic maps have been drawn branch by branch, and yet the first steps, the spark that set petals upon the green world, are not entirely clear. The scents and colours that rule whole landscapes in spring still carry the stamp of a beginning we have not fully glimpsed. Grasses invented a clever way to feed on light in lean air, routing carbon through a pathway that wastes less when heat is high and water is scarce. This trick, taught in classrooms as a set of letters, evolved not once but many times. Why some lineages found the switch and others did not remains an open problem, and the details of how a set of enzymes and chambers in a leaf reorganized across ancient climates is still being learned, leaf by leaf. The height of trees invites patience. Water climbs a column of wood not by a pump at the roots, but by pull at the top, as molecules leave the leaf and tug on the chain below. How high that chain can hold without snapping is set by physics and by the micro-architecture of xylem. Yet in the tallest groves, where crowns comb fog from Pacific winds, the fluid mechanics edge into limits we only approximate. There may be subtle valves, microstructures that close under tension and open again that we have not fully captured in equations. Ice ages arrived like slow tides across the bones of continents. More than once our world wore white down to the tropics, the exact trigger that pulled ice so far from the poles, the touch of volcanoes purring for centuries. the breath of the ocean restoring carbon in the deep, the long dance of the planet about the sun, and how biology responded to thicken or thin clouds, remains a set of mysteries that climate scientists refine with each new core of sediment they raise from the sea floor. The great blooming of animal forms in the Cambrian seas looks quick in stone, in a span that would be long by human measure, yet brief on a geological clock. Shells and eyes and spines appear across the record. The engines of this bloom have names: oxygen, predation, gene toolkits that enable new shapes, yet how these threads braided into that particular wave is still discussed softly in halls where fossils sit in drawers like grey paper lanterns. The passage from single cells that lived alone to communities that decided to remain together was crossed more than once. Slime molds do it during a day, bodies that merge and then separate. Certain algae practice simple cooperatives. The route to a body that could make organs and mend wounds is a longer road. What set that road, what locked partnerships into rules of division of labor firm enough to last for millions of years, stays partly hidden in the past. The language cells used to promise fair shares of work and reward is still being translated. There are animals that shrug off cold by making a kind of glass inside their cells, and others that let ice form in spaces between them, holding tissues safe until spring. The chemistry of this hard piece is used to save organs for surgery. Yet the full map of how ice and membrane and protein dance together has steps we do not yet know. In deserts, tiny seeds can sleep for decades, then wake at the first scent of rain, as if counting the years. What the clock looks like to a silent embryo in soil is a question laid gently upon the field. Cancers are not a single foe. In whales with huge bodies, the math of many cells should bring many tumors, yet they seem to carry quiet shields we have not fully copied. In naked mole rats, the tissue itself rejects runaway growth, as if the walls were stronger by design. The logic by which a tumor chooses to wander, to leave its home and create a new colony within a body that does not welcome it, remains only partly charted. Each time we think we have a rule, a new exception walks into the room. Brains grow minds that see out through eyes, but a cephalopod carries much of its thinking in its arms. A worm regrows a head and remembers a lesson it learned before the cut, and a bee seems to count to a small number and perhaps even notice 0. Intelligence may come in many shapes and speeds. Our models have been drawn mainly from a single branch, our own. The full tree of minds is broader than that, and its branches are still being traced. People fall into sleep, a state as necessary as water and food, and we still do not hold the whole purpose in our hands. The brain replays, prunes, and strengthens connections in sleep. It cleans its intercellular spaces, as if flushing streets after a festival. Dreams build narratives, sometimes wild, sometimes healing. But why some rules of language are practiced, why some fears are faced, why certain memories are folded deeper while others are let go, is a set of questions that continue to float like lanterns at the edge of a lake. During waking hours, a placebo can set pain at a lower note, and the body does obey belief in a way that is not illusion but chemistry. The mirror image of that a nocebo can harm by suggestion alone. Clinics know this, and yet the deep pathways from expectation to molecule, from story to immune cell, are not all mapped. In trials, sham treatments change heart rates and hormone levels, and the degree to which trust can heal remains both powerful and slightly mysterious. Language grew in the throat and the hand, in the eyes that watch faces, in the ears that learn rhythm. Children pick up grammar with ease that language teachers envy. Whether there is a single shared skeleton of rules beneath all tongues, whether words first hung on gestures and only later learned to fly by voice, whether music is an elder sibling or a cousin to speech, all remain friendly arguments in the halls of linguistics. We close this stretch with a look at culture outside our species. Crows drop nuts at crosswalks and wait for the light. Orcas teach their young new hunting techniques. Meerkats turn scorpions into safe meals for pups, removing stingers with practiced care. Culture, that word we once kept for ourselves, travels in many families now. How widely it moves, how deep it goes, how it shapes genes across generations. These are riddles. The field is now bold enough to pose and patient enough to answer slowly. The night is long and mysteries are plentiful. Each of these puzzles is a quiet invitation, not a wall. They are reasons to watch, to measure with care, to keep the tone of curiosity kind. As the tide of the documentary flows onward, the questions will continue to unfold, always with the same gentle promise that not knowing is not failure. It is the place where learning takes its first breath. The night deepens and we return to our quiet journey, letting the mind drift like a small lantern boat on a broad river. The ocean of unanswered questions widens ahead, and our task is simple and soothing: to look, to wonder, and to enjoy not knowing everything yet. Let us move gently from living swarms to deep mathematics, from whispering molecules to machines that learn, keeping the same calm breath as we go. Bees perform their moving geometry on sunlit combs. The dance carries two messages at once: distance and direction, and often a hint of quality. The angle of the waggle with respect to gravity tells where the flower patch lies with respect to the sun, even when the sun hides behind cloud. The length of the waggle run tracks how far to fly. Yet the code is not entirely fixed. It drifts with temperature, time of day, and the landscape the bees have learned. Different colonies appear to speak with slightly different accents, and young foragers learn by watching older guides. What exactly counts as a unit of distance in this choreography, and how a mind the size of a sesame seed performs such vector arithmetic remains a warm puzzle. Ants move like a single creature made of thousands of bodies. A colony can choose the shortest path between nest and food using only local rules, can divide labor without a manager, and can build air-conditioned towers out of grains of soil. The recipe hides in feedback. A little trail of scent draws more feet, and more feet strengthen the trail. But the full intelligence of a colony is not only chemistry. Ants change their rules with age, season, and need. They vote with head bumps and food sharing, and sometimes they simply pause, as if waiting for a rhythm we do not hear. Where exactly does the decision live when no single ant knows the plan? Reefs glow at dusk, and we call them forests of stone. Why some coral communities resist heat and disease, while their neighbors bleach and crumble, remains partly hidden. Genes matter, and so do the algae they partner with, and so do tiny microbes on their slimy coats. Currents can bring cool pulses, turbid water can shield harsh light, and a short history of small stress can act like a vaccine. The recipe for resilience is a layered story, still being written by currents, by weather, and by the minute choices of countless cells. A worldwide amphibian disease arrived like a cold fog. The fungus that coats frog skin does not kill every species in the same way. Some carry it like a mild itch, others fall silent within days. Temperature, salt in the water, the community of skin microbes, and the strength of the immune system all shift the balance. Yet identical conditions can lead to wildly different fates. Somewhere between gene and environment lies an uncharted map of defense, and we are still learning how to read it. Tardigrades walk like patient bears across crystal deserts. When water vanishes, they fold their legs, curl their bodies, and turn syrupy inside, trading motion for long safety. Proteins that form glass, like shields and coils of special sugar, protect membranes and fragile strands of heredity. They can wake again after years, shrugging off vacuum, cold, and high radiation. We can list the molecules, but the deep choreography of the so-called ton state, molecule by molecule, minute by minute, has not yet been filmed by any camera we own. The molecular clock was meant to tick evenly across the tree of life, letting us date branch points by counting changes. Yet the clock runs fast in some lineages and slow in others. Body size, generation time, metabolic temperature, and the strength of natural selection all push the hands. And sometimes the mutation rate itself mutates. We correct and recalibrate, but beneath the statistics, a simple mechanistic picture is still missing, like the gear train behind the face of a watch. Imprinting carves early experience into the nervous system. A hatchling goose will follow the first moving thing it sees and will keep that choice like a seal on wax. In people, something similar happens when a newborn learns the sound and smell of a parent. Hormones and critical windows matter, as do certain brain regions, but the precise code that turns a single early event into a lifetime bias is still misty. Phantom limbs remind us that the map of the body is drawn inside the head. After an amputation, people may feel an itchy hand that is no longer there. The cortex retains its old neighborhood plan, and nearby regions invade the open space. Touching the face may be felt as a touch on the absent fingers. Mirrors can ease the pain by giving the brain a picture it can accept. But why some phantoms ache while others simply feel present, and why the trick with the mirror works for some and not for others, are questions that keep physicians and philosophers gently awake. There are rare minds that recall a year day by day, or calculate calendars as if time were a landscape. There are painters who can recreate a city after one helicopter ride, and musicians who can play a symphony after a single hearing. Sometimes this talent appears alongside difficulty with ordinary life. Brain scans show unusual connections, but a general recipe for such islands of skill remains unsettled. We all know the moment when an answer appears like a small door opening. Creativity can arrive in the shower, on a slow walk, or as we fall asleep. It favors minds that can hold contradictions softly and can keep several frames of reference alive without forcing one to win too soon. Sleep reorganizes memory, and wandering attention lets distant ideas shake hands. Yet there is no single switch marked insight. The brain seems to use many paths to the same clearing and many clearings to the same idea. In physics, there is a quiet winter tale. Certain ceramic compounds drop their electrical resistance to nothing at temperatures far warmer than the old metals that became superconductors only near absolute zero. Magnetic fields arrange themselves in mysterious whirlpools, and electrons appear to pair in ways that do not fit the classic picture. We can draw phase diagrams and measure beautiful curves, but a single simple theory that predicts which crystal will show this magic is still out of reach. Turbulence is the unruly dance of air and water. Smoke that starts as a smooth ribbon breaks into eddies, and then those eddies breed smaller eddies, and so on until the flow turns into a crowded city of swirls. Engineers can simulate and pilots can respect it, yet a full mathematical description that explains why energy cascades the way it does remains a long-standing invitation to clever minds. The wave function in quantum theory spreads possibilities like dew on grass, and a measurement leaves only one wet blade. Does a physical process reduce the many to one, or is the collapse only a bookkeeping step in our heads? Modest experiments keep poking at the boundary between the small and the human scale, looking for a place where the fog clears. So far, the fog itself looks like part of the landscape. Entanglement ties two particles into one story that distance cannot unravel. Change the state of one and the other responds in a way that respects statistics and yet defies a simple picture of cause and effect. Could such ties let influence travel backward in time, or are they only patterns in correlations with no whisper of message? Nature keeps giving the same calm answer. No usable signal rides this thread, yet the thread exists, strong and strange. In computer science, there is a riddle with very practical teeth. Some problems are easy to check once a candidate answer is given, yet desperately hard to solve from scratch. Are these two kinds of difficulty, in fact, the same? If they are different, then many hopes for shortcuts vanish. If they are the same, then many locks on our digital world would, in principle, open at once. Decades of work have not settled the matter. The number line holds its own mysteries. The Riemann hypothesis hides in the music of the primes, claiming that their rhythm follows a single critical line if you write the right complex tune. It would explain why primes thin out just so. Mathematicians keep finding new hints, like shadows pointing toward the same narrow path, but a complete proof stays just beyond the next ridge. Other conjectures stand like distant hills in the same landscape. The Collat's rule takes any whole number, applies a simple fold and stretch, and repeats. Every number ever tried eventually slides down to 1. But no one can show that all numbers must obey. The Goldbach thought claims every even number beyond a small start is the sum of two primes. Numerics nod in agreement. Proof remains shy. The Navier-Stokes equations describe viscous flow with elegant symbols, but whether smooth solutions always exist in 3 dimensions, or whether they can blow up like thunderheads, is still unknown. Even the digits of the number pi tease us. Do its infinite decimals contain every finite pattern, making it a kind of numeric library, or does some subtle bias lurk inside the apparent randomness? Now we step from chalkboard to circuit. Could a built machine ever feel the way a person feels when a melody rises or a memory stings? Consciousness might require a special kind of global workspace in the brain, or a certain rich loop of information that refers to itself. Or it might be something that emerges when a system models its own modeling. We can build networks that label pictures and write songs, but whether any of them has an inner scene is still an open and very human question. Learning systems work often surprisingly well and still behave like black boxes. They capture regularities in mountains of data and then deliver accurate answers without telling us which clues mattered. Some success rests on simple statistics, some on internal representations that look like maps, some on layers that form detectors we never thought to design. We move toward methods that explain themselves, yet true transparency remains rare. Patterns appear across many fields. Power laws and heavy tails show up in city sizes, earthquake energies, word frequencies, and network links. Why does the universe prefer these long-tailed distributions? Sometimes we can derive them from growth with rich get richer rules, sometimes from multiplicative processes with noise, but a single unifying story is still forming. At very small scales, matter behaves like a crowd that has agreed to move together. You can shake a box of self-propelled rods or living bacteria and watch them form swarms, lanes, and vortices that resemble the phases of crystals and fluids, except they use fuel to keep order alive. This active matter lives between physics and biology. We know how to describe the endpoints, not yet the full conversation. In particle physics, there are hints that something new is waiting in the wings. A few experiments have seen small deviations from expected rates or unexpected asymmetries in the decay of short-lived particles. The differences are tiny and easily swallowed by statistical noise, yet they appear in more than one place. Each hint asks whether our current theory is a nearly complete map or only the careful drawing of one valley in a larger country. Some metals remember their childhood shapes. A wire can be twisted and bent, then warmed to return to the exact form it had when it was first born from the mold. The reason lies in the march between two crystal structures with very different symmetries. Yet the fine details of how microstructure stores a three-dimensional memory remain an active field where physicists and engineers trade stories like watchmakers. Topological insulators are solids where the inside stays quiet while the edges sing. Electrons on the surface act like special guests who cannot be bumped off the dance floor by disorder. The reason is deep symmetry. But the full catalogue of topological phases and the best ways to tune them for devices is still being written like a new atlas. Quantum computers promise to factor large numbers and simulate complex molecules by using the full space of quantum states. The problem is that the world touches any delicate state and it collapses back into ordinariness. We frame codes that can correct errors, and we build logical qubits out of many physical ones. But the road to a truly fault-tolerant machine with practical scale remains long, with unknown hairpin turns. Quantum teleportation moves the state of a system from one place to another using entanglement and a pair of ordinary messages. It does not move matter, and it does not beat the speed of light, yet it moves what matters about a quantum system. Its identity in the language of amplitudes. The limits of this trick and its best uses in a future quantum internet are still being mapped. When the mind tires of hard edges, it is pleasant to return to softer mysteries. Why does a swarm of starlings turn like a single thought across the sunset? Why do people clap in unison after a concert and then drift back into irregular noise? Why does a crowd of strangers in a square sometimes begin to sing? The mathematics of synchronization is rich, and yet the feeling of a system settling into one rhythm still feels like a kind of magic. In all these questions, the common thread is not failure, but invitation. The unknown is not a wall, it is a path lit by small lanterns. Each question we touched tonight, from the waggle of a bee to the deep symphony of equations, is both a frontier and a lullaby. Scientists lean into them all day, and then, as evening arrives, they set them down gently and let them glow on the bedside table of the mind. If you feel your breath deepening and your thoughts loosening, that is fitting. Curiosity does not demand that we stay awake. It stays awake for us, keeping a light by the door until morning. Below the seafloor and beneath the deserts, there is a second world of life that continues to unsettle researchers. Microbes live not only in the pores of deep sediments, but also inside hard basalt, surviving on faint chemical gradients where sunlight never reaches. Estimates suggest that this deep biosphere might hold a significant fraction of the planet's total microbial cells, yet no one can specify the true inventory or the upper limits of temperature and pressure that life can endure. Samples from kilometers down in boreholes wake when given water and trace nutrients, as if time there moves differently, and questions multiply. How slow can metabolism be and still qualify as living rather than merely waiting? How often do these cryptic lineages exchange genes with surface relatives? Could ancient metabolisms, long erased above, persist in the rock record below? The deep biosphere feels less like an exception and more like a fundamental layer of the planet that we have only begun to map. From that unseen world of microbes, we step toward a different riddle at the origin of complex cells. Somewhere in deep time, a bacterial cell and an archaeal cell forged a partnership that produced the ancestor of all animals, plants, and fungi. The mitochondrion within our cells is the fossil of that event. A former bacterium that took up residence and began paying its rent with energy. Yet the choreography is still mysterious. What ecological setting brought the partners together? Which genes moved first, and why did the host relinquish control of so many essential pathways to a tiny battery with its own genome? Some lineages also harbor plastids from an endosymbiosis that happened later, implying that the path to complexity is not a single lucky accident, but perhaps a staircase of mergers that we do not yet know how to climb in the laboratory. Until we can replay that transition, even in outline, the birth of our kind of cell remains a partly told story. The next puzzle is even more intimate. Sexual reproduction with meiosis and recombination seems to carry obvious costs. One must find a partner, combine genomes, and accept the reshuffling of traits that might have worked well as they were. Why then did sex spread so widely across the tree of life? Explanations invoke the repair of DNA damage, the purging of harmful mutations, or the faster assembly of beneficial combinations. Yet each idea explains only some of the observations. The distribution of asexual lineages, the persistence of ancient sexless clades, and the odd cycles of organisms that switch seasonally between modes all leave gaps. We know that sex changes evolution's pace. We still do not know exactly why evolution selected sex in the first place and why it keeps paying for the ticket. When we fast forward to the Cambrian chapter, we meet another case of sudden abundance. Over a geological blink, many body plans appear in the fossil record, complete with eyes, armor, claws, and complex guts. Was this an artifact of preservation, a consequence of oxygen rising, a cascade of ecological arms races, or a biological toolkit unlocking new possibilities? Most likely it was a choir of causes singing together, but the score is incomplete. The most perplexing verse is the speed at which intricate eyes emerged in several lineages. Did light-sensitive molecules and simple pits already exist for hundreds of millions of years, waiting for a nutrient or oxygen threshold to finally cross? The answer is still tucked within shales and the genomes of humble marine worms. Jaws, limbs for walking on land, and wings for flying grew from similar mixtures of opportunity and constraint. Vertebrate jaws probably evolved from gill arches, yet the intermediate steps remain few in stone. Fish that explored the shallows left tracks that look like footprints, then bodies with robust bones and wrists, yet why that leap happened when it did is debated. Insects invented flight far earlier than birds, with delicate wings that may have started as heat dissipators or gliding surfaces on juveniles. But no living insect shows a halfway device, and the genetic circuits that specify wings look older than wings themselves. Evolution often hides its ladders after it climbs them. Flowering plants burst onto the scene later and transformed the planet. Darwin called their abrupt rise his abominable mystery. We can trace the genetics of pigments and scent, of nectar and seed, yet the tipping points that accelerated their diversification remain elusive. Perhaps it was the co-evolutionary embrace with pollinators. Perhaps changes in climate or soils gave them new rooms to inhabit. In a world thick with their descendants, we still do not know why they triumphed so quickly. The rhythm of extinctions is another enigma. The end Permian catastrophe is linked to enormous volcanism and climate disruption, but the exact sequence of dying is disputed. Some geochemical clues point to anoxic and sulfidic oceans, others to extreme heat, others to a cocktail of stressors that arrived in waves. The end Cretaceous impact finished the non-avian dinosaurs, yet why some groups survived and others did not is still argued. In the deep sea where sun never reached, many lineages continued as if nothing had happened. Did food webs there have hidden resilience? The fossil record answers in images and layers, not in complete sentences. Geophysics offers its own questions. Plate tectonics sets Earth apart from its siblings and shapes climate and life, but we do not know exactly when the engine started or what lubricant allowed plates to slide. Some models require large amounts of water in the mantle. Others require a hotter and weaker lithosphere in the Archean eon. The two massive, low shear velocity provinces deep under Africa and the Pacific look like continents made of different stuff. Yet their composition and origin remain speculative. They might be piles of ancient oceanic crust, or the ghosts of early mantle differentiation, or something we have not named. Far below those structures sits the inner core, sometimes reported to spin at a slightly different rate than the mantle above, sometimes reported to pause or reverse that drift. Our longest thermometer remains opaque. At smaller scales, nature keeps teasing with phenomena that feel simple and stay stubborn. Ball lightning has been reported for centuries, sometimes inside airplanes, sometimes drifting through rooms. Laboratory attempts produce cousins of the effect. But a reliable recipe is missing. Rogue waves appear from calm seas as transient giants and disappear before instruments can tag them. We know seafloor landslides can trigger tsunamis and that currents running along steep bathymetry can focus energy, but the precise cocktail that births a one in many thousands wave at a specific hour is rarely captured. Climate carries puzzles that are not only academic. The seesaw of monsoon strength and the reason vast deserts flip between green and arid in cycles of tens of thousands of years involve deep couplings between ocean circulation, vegetation, dust, and slow wobbles of Earth's orbit. We can replay past transitions in models and match many features, but we still lack the confidence to predict exactly when a present-day threshold might be crossed. The story of El Niño and La Niña likewise is readable in corals and sediments going back many centuries, but the full control panel of the tropical Pacific remains partly unlabeled. The origin of life sits at the center of the greatest unknowns. We can synthesize amino acids and nucleotides, make fatty bubbles that divide, and coax ribozymes to copy short strands. We have not yet built a self-sustaining cycle that turns geochemical energy into heredity and open-ended evolution. Was the first information molecule a form of RNA? Did peptides and lipids arrive first and then invite nucleotides to the party? Did life begin in warm ponds, in alkaline vents, in icy brines, or even inside porous rocks that acted as natural reactors? Each option has strengths and gaps, and the earliest traces have been overwritten many times by heat, pressure, and oxygen. Even once life begins, the choreography of large innovations is unclear. The last universal cellular ancestor left whispers in every genome, yet the details of its metabolism, its membranes, and its environment are contested. We do not know why biology chose one-handedness for amino acids and the opposite-handedness for sugars. Physical processes can bias chirality, but amplifying that tiny bias to planetary dominance is not yet demonstrated outside the imagination of models. Viruses complicate the border between life and chemistry. They borrow cellular machinery, yet craft strategies so inventive that biologists debate whether they are escapees of ancient cells, degenerate descendants of cellular parasites, or primordial replicators that predate cells. Giant viruses with hundreds of genes blur the line further. Prions go farther still, passing on shape rather than DNA, and showing that information can live in the fold of a protein. Inside animals, the mind builds mysteries that resist simple mapping. Sleep costs precious foraging time and invites danger, yet evolution has preserved it across birds, reptiles, mammals, and even small invertebrates. Some marine mammals sleep with one hemisphere at a time, showing that sleep is more flexible than we guessed. Dreams are even harder to anchor. They resemble rehearsal, therapy, and cleaning all at once. Memories settle into long-term storage, yet the exact cellular grammar of that consolidation is only lightly sketched. Consciousness appears as a flicker of coordinated activity across networks, but no consensus theory converts spikes and synapses into the feeling of a present moment. Physiology has riddles in the immune system, which sometimes turns on the body it protects. Why certain tissues become targets, and why only some people carrying the same genes develop disease, is still being unraveled. Cancer metastasis likewise contains an unsolved preface. Tumors shed cells all the time, but most travelers die. A very few find a niche, switch identities, recruit blood vessels, and grow. The set of signals that lets a roving cell feel at home is not yet fully catalogued. Longevity and its strange outliers leave us curious and a little envious. Hydra show negligible senescence. A small jellyfish can revert from an adult to a juvenile state. Some mammalian relatives resist cancer or tolerate low oxygen with grace. If aging is a network of processes, we are still missing several nodes and links. Regeneration multiplies the wonder. A salamander can rebuild a limb, including bone, nerves, and skin. Mammals attempted the same trick only in a few limited contexts. The suppressors of regeneration may be as interesting as the genes that enable it. The senses astonish with talents that border on the invisible. A few humans hear colors or taste shapes. This synesthesia appears to have both genetic and experiential roots, suggesting that wiring diagrams in the cortex are plastic in ways we only partly grasp. The feeling of having seen a moment before, the familiar déjà vu, may involve a brief mistiming between rapid and slow pathways, but the brain does not reveal its metronome. The reason some people recall everything from a specific day decades ago while others cannot is yet another riddle of encoding and retrieval. Animals add their own riddles. Bees dance to tell nestmates where flowers are, yet the full language of distance, direction, and quality is still debated. Ant colonies behave like a single creature with a distributed brain. Simple rules at the individual level produce a collective that allocates labor, regulates temperature, and mounts defenses. In coral reefs, some communities resist heat and acidification better than neighbors, implying hidden genetic reservoirs or microbial allies that we have not fully identified. A fungus spreading across continents kills many frog species but spares others. The reasons range from skin chemistry to behavior to microclimate, and the ranking of causes is not settled. Evolutionary clocks tick at unequal rates. Some lines accumulate changes quickly, others scarcely change across very long spans of time. We use molecular clocks to date branching events, but the clocks speed up and slow down for reasons that go beyond body size or generation time. Genomes are restless landscapes. Transposable elements copy and paste themselves, weaving junk and potential into introns and regulatory deserts. They can jump in bursts during stress and then go quiet. Why genomes tolerate so much wandering code is a continuing question. Navigation without instruments continues to fascinate. Monarch butterflies reach a very specific mountain range, even though the individuals start the trip never having seen the destination. They appear to carry a clock, calibrated by sunrise and sunset, and to read the polarized pattern of the sky. Sea turtles cross entire ocean basins and return to the beaches where they were born, probably using a magnetic map with features finer than we expected. Birds sense magnetic fields through a quantum-sensitive chemical in the eye. But disentangling that quantum chemistry inside a warm, living retina is a tough experiment. In the physical sciences, turbulence remains the archetype of an equation that works and a behavior that surprises. We can write the equations of fluid motion and solve them for many cases, yet predicting the exact statistics of whirls and eddies at all scales is still beyond reach. Superconductivity at relatively high temperatures is another open front. Certain ceramics carry current without resistance far above the temperature of conventional conductors, but the glue that pairs electrons remains contentious. In mathematics, the list of open problems is a constellation that refuses to fade. Whether difficult problems can be solved quickly, whether a famous function that encodes the distribution of prime numbers zeroes out precisely on a critical line, whether every even number beyond 2 is a sum of 2 primes, and whether certain smooth flows can avoid singularities are all compass points where proof has not yet set foot. The current age brings new puzzles from technology. We can build learning machines that excel at recognition and strategy, yet their internal logic is often a shadow play of weights and activations that defy fluent explanation. Patterns such as power law distributions appear repeatedly in language, cities, earthquakes, and finance, suggesting common mechanisms of self-organization. The lines between physical systems, biological collectives, and social networks blur, and new mathematics is being written to thread them together. Human origins keep adding branches and footnotes. Our species emerges from Africa with a mosaic of traits and behaviors rather than a single spark. Cousins such as the Denisovans left only fragments of bone and a strong genetic signal in living people. The peopling of the Americas looks less like a single land bridge crossing and more like a sequence of pulses along coasts and rivers. Languages carry clues to deep migrations, but their family trees twist and the roots are contested. Even the origins of music and color words point to rich interactions between environment and culture that we still debate. The oceans return near the end of this quiet journey because they hide half of the remaining mysteries. How much life really lives in the abyssal night, why some blooms of plankton reach colossal scales and others fade, where eels breed and what map they follow, how internal waves lofty as mountains break and feed nutrients toward the light, why whale falls can nourish communities for decades, and what decides when the feast ends. Each question reminds us that most of our planet is still a frontier. Across all these topics, a gentle pattern appears. Science does not avoid mystery. It cultivates the unknown the way gardeners cultivate soil. A question is not a failure to explain, but the beginning of a map. We keep returning to the same themes because they matter to how the world works and to how we live in it. Why life began and how it persisted in the dark. How planets form and how climate swings. How minds make meaning from sensation. How simple rules create complex order. The list reaches 200 and could reach 2,000 without exhausting the curiosities waiting in rocks, genomes, clouds, and stars. As you settle toward rest, imagine each unsolved question as a small lighthouse in fog. Each casts just enough glow to show a bit of coastline. Together, they trace an archipelago of places we will one day explore more fully. Between those lights lies darkness that is not hostile, but simply quiet and patient. In that quiet, the work of discovery takes a long breath. And in that breath, the mind can drift, not with frustration, but with the soft wonder that keeps us looking again tomorrow. The farther we walk into the unknown, the more softly the questions begin to speak. You can hear it in the air itself as it warms and cools in ways we are still learning to read. Climate sensitivity, the response of global temperature to a doubling of carbon dioxide, has a name that sounds simple, yet it is a choir of feedbacks that do not sing in unison. Clouds shift their mirrors, water vapor thickens the blanket, ice retreats and reveals darker oceans that drink sunlight. Paleoclimate hints from ancient shells and trapped bubbles say the response could be several degrees, but the exact number floats with the clouds. Some models lean toward a gentle nudge, others toward a stronger push. The truth is likely a range that depends on the state of the system, the patterns of warming over different oceans, and the behavior of clouds that remain the most secretive actors in the play. Those clouds have accomplices, tiny particles known as aerosols that float like motes of dust in a cathedral beam. They can brighten clouds by seeding more and smaller droplets, which makes the clouds reflect more light. They can also darken the planet when soot falls on snow. The same aerosol might cool in one region and warm in another, depending on height, humidity, and the company it keeps. We can measure many of these particles, yet their sprawling catalogue of sizes and chemistries means that the final effect on climate still comes with wide ribbons of uncertainty. It is as if the atmosphere were a grand kitchen where innumerable spices drift and mingle, and we are trying to guess the flavor of the stew while it is still simmering. From that uncertainty springs a question that sounds practical and feels perilous. Could humanity deliberately shade the planet to buy time while it cleans up its emissions? Proposals exist. Some imagine brightening marine clouds by spraying sea salt. Others picture a thin veil of reflective aerosols in the stratosphere, echoing the cooling after a very large volcanic eruption. There are ideas to fertilize parts of the ocean with iron to coax plankton blooms that would pull carbon downward. Each path comes with trade-offs. The stratospheric veil could change rainfall patterns. The iron could shuffle marine food webs in ways that last generations. Stopping any deliberate cooling after years of use could provoke a rebound that is too abrupt for societies and ecosystems. The very act of testing at scale becomes its own ethical inquiry. We do not yet know how to cool without consequences. While we worry about the heat, the desert sends a gift to the rainforest. Each year, winds lift dust from the Sahara and carry it across the Atlantic. In that dust are trace nutrients, especially phosphorus, that the ancient soils of the Amazon have lost to rain. The sky becomes a bridge that feeds trees. The flux is not constant. It changes with rainfall in Africa, with the tilt of the seasons, with the growth and decay of vegetation across continents. Some years the air delivers a feast, some years a fast. The rhythm is large enough to be mapped from orbit, yet the full balance sheet that connects dust storms, ocean plankton, and forest growth is still being assembled. Lightning writes other puzzles in the sky. High above the main bolts, ghostly forms flare and fade, red sprites and blue jets and elves that shimmer for a heartbeat. At the same time, detectors on the ground pick up sudden bursts of very energetic radiation. Just as a storm discharges, the atmosphere for a moment becomes a particle accelerator. We know that strong electric fields can speed electrons and that collisions can create bright flashes of gamma radiation. But the details of how a particular cloud stack with a particular mix of ice and water decides to unleash such bursts are still being traced. The quiet lives of trees hold their own riddles. A forest can endure repeated droughts and then fail in one dry season that looks similar on paper. Trees appear to sense not only present moisture but also near future stress, opening or closing stomata as if they calculate the odds of survival. Hydraulic thresholds inside trunks stored carbohydrates, the company of mycorrhizal partners in the soil, and the genetics of leaf design all play a part. No single line on a graph can yet tell us which stand will tip and which will hold. Insects migrate along invisible highways in the sky. Radar screens light up with moving bands that shift with the season. Butterflies and hawk moths and dragonflies appear to use tailwinds at specific altitudes and may even climb until they find them. Some navigate by the position of the sun or by polarized light. Some seem to tune to faint cues of magnetic inclination. Across continents, trillions of small bodies rise and fall like a respiratory cycle of the biosphere, and we are only beginning to chart the routes and understand the signals that guide them. Pollinators have been declining in many regions, but the story is not a single thread. Land use changes erase wildflower corridors, parasites weaken colonies, pesticides add their own pressure, climate mismatches desynchronize blooms and visits. Light at night confuses navigation. In some places, native pollinators remain stable when landscapes are kept diverse. In others, a cascade of small stresses adds up to a silence in orchards. The science is like a field notebook with many entries, some in bold ink, many still in pencil. Beneath our feet, soils hide vaults of carbon. A single handful can hold more living cells than there are people on Earth. They knit carbon into aggregates, they pry it loose, they breathe it back. Disturbance, heat, and moisture rearrange those balances. There are hints that adding certain mineral amendments, encouraging fungal networks, and keeping living roots in the soil most of the year can thicken these vaults. Yet the rates and limits differ by climate and parent rock, and we are still learning how to help the soil keep its treasure for centuries rather than seasons. In forests at night, some mushrooms shine. A soft green light seeps from gills and caps. Bioluminescence on land is rarer than in the sea, and its purpose is debated. It may attract insects that ferry spores. It may be a glow that escapes from biochemical housekeeping, or it may even deter grazers that do not like luminous meals. In a few experiments, insects show clear attraction to glowing caps. Yet the full map of who benefits from this midnight advertising remains incomplete. Medicine tells quieter mysteries. Now and then a severe disease retreats with no therapy that could reasonably explain the timing. The vocabulary tries to keep dignity and caution by calling this spontaneous remission. The immune system can rally in unexpected ways. Tumors can lose their blood supply. Infections can awaken responses that overreach in beneficial directions. Each case is a story, and patterns are very hard to isolate because the events are rare and the temptation to attach false causes is strong. The careful cataloguing continues because even a small hint could teach a larger therapy. The same drug can be a lifeline for one person and a whisper of help for another. Differences in how liver enzymes work, in how transport proteins move molecules across barriers in the shape of receptors and ion channels, and in the activity of the microbiome all change the experience of a medicine. We are turning this patchwork into pharmacogenomics and personalized dosing, yet the map contains many blank squares. The line between variation and predictability has not become crisp enough for routine care in many conditions. A single smell can unlock a cascade of memory and feeling. The chemistry is a cloud of similar molecules, often made of the same atoms shuffled in space. Two mirror image forms of a molecule can smell utterly different. A reminder that olfaction is geometry as much as formula. The receptors in our noses act like an orchestra that can play many chords from the same set of notes. Why some people perceive a scent as heavenly and others as sharp is a mix of receptor genes, previous experience, and cultural vocabulary. The exact path from a shape at a receptor to a feeling in the mind is still traced with dotted lines. Our internal clocks differ. Some people feel alert at dawn and soft by evening. Others come alive when the city quiets. Genes in the molecular gears of circadian rhythms, light exposure during early life, and habits of sleep and work all nudge the hands of these internal clocks. Yet we cannot fully predict who will be an early lark and who will be a night owl, nor can we easily shift a clock without side effects that ripple through metabolism and mood. Some people hardly shiver when others bundle in coats, brown fat that burns energy to make heat, the efficiency of peripheral blood vessels, the thickness of subcutaneous fat, and even adaptations of the nervous system all matter. Training in cold water can reshape the response, but the range of natural differences remains an open atlas. Hidden inside our genomes are the fossils of ancient viruses. These long threads inserted themselves into the germline of our ancestors and rode into the future as passengers. Some now act as switches that regulate our genes. Some may have contributed to the evolution of the placenta. Others are linked to disease risk. How these ancient viral notes are played or silenced in different tissues and how they influence conditions from cancer to immune disorders is still being untangled. Neurodevelopmental conditions invite careful humility. Autism likely arises from many roots that converge on changes in how brain circuits wire and prune. Hundreds of genes contribute small nudges. Environmental factors, such as maternal inflammation or very early exposures, add context. The ratios of diagnosis climb in part because awareness and screening improve, yet the diversity of autistic experience and the variability of support needs make one-size-fits-all explanations impossible. The science is moving toward understanding circuits and personalized supports while it resists oversimplification. Schizophrenia carries voices and visions that feel as real as the touch of rain, and it carries negative symptoms that flatten energy and will. Many genetic factors of small effect add risk, and disturbed connectivity between frontal and temporal networks is common. Yet the spark that ignites the first episode differs. Stress, substance use, sleep disruption, and social isolation can all be matches. The precise path from altered synaptic pruning during adolescence to the language of hallucination is still being charted. There are repeated hints that creativity and bipolar tendencies sometimes share ground. Bursts of energy and divergent thinking can arrive together, and family studies show clustering of artistic achievement and mood disorders. This may be a statistical echo rather than a rule, and we must treat such patterns with care to avoid romanticizing illness. The neural and genetic threads that would tie novelty seeking to mood cycles are not yet strong enough to bind a theory. A small fraction of people experience extraordinary sensitivity. Some see colors with greater richness. Some can distinguish thousands of scents with ease. Sometimes extra receptors are present. Sometimes cortical areas devote more territory to a sense. The world is not equal across individuals, and our instruments have only begun to match what some noses, eyes, and ears can do. On the edge of what science can measure are reports of unidentified anomalous phenomena. Most events resolve into familiar things once data improve. A planet seen through turbulence, a balloon in a strange wind, a glint on a camera sensor. Yet a small set of occurrences recorded by multiple instruments keep their mystery. The goal is not to rush to extraordinary claims, but to collect extraordinary quality of evidence. Filters are tightened, algorithms are made transparent. With patience, the unknown shrinks, though a few traces remain to keep our curiosity honest. Sometimes the atmosphere booms like a drum with no visible stick. People hear single loud reports that travel far. Candidates include very high altitude meteors, sudden releases of pressure on temperature inversion layers, and rare ducting of sound that lets distant explosions arrive as if from nowhere. The recipe may differ from night to night, which is why the notes on this score are still penciled rather than inked. The aurora usually glows in green curtains, yet there are nights when a stable red canopy hangs like a luminous ceiling. These stable red arcs live very high in the thermosphere, where oxygen glows in crimson when excited by flows of charged particles and changes in electric fields. There is also a more recent friend in the sky, a mauve ribbon nicknamed Steve, which appears with a thin green picket fence. Steve is not a classical aurora. It seems to be a narrow river of very hot plasma rushing through the upper atmosphere. Exactly how energy from the magnetosphere focuses into such delicate structures is still a fresh story. Deep mines and desert valleys sometimes glow with light that seems to come from the air itself. Piezoelectric strains in rocks before earthquakes, triboluminescence when grains rub, and chemical reactions that emit photons are all on the list of suspects. Some reports correlate with tectonic stress, others with no clear trigger. The result is a handful of natural lightworks that defy easy categorization. On winter lakes, near perfect circular rafts of ice slowly spin, the disk forms where a gentle vortex in the current erodes the edge into a circle, and the slow rotation keeps it shaved smooth. But the origin of the precise vortices remains site-specific. A fallen log here, a bend in the bank there, the viscosity of near-freezing water, the thickness of fragile ice, all can combine under the right chill to sculpt a turning coin of winter. In Costa Rica, hundreds of nearly perfect stone spheres rest in fields and gardens. Many were moved from their original context, so the story they once told is fragmented, carved from granite and other stones. Some large ones would have required remarkable organization to cut and transport. They may have been status markers, cosmological symbols, or boundary stones. Without inscriptions to guide us, we read them by shadow and guesswork. Singing dunes hum in notes as deep as a foghorn when dry grains avalanche. The sound arises when many grains slide together and their collisions line up in phase, turning billions of tiny taps into a single musical tone. Each dune has a preferred note that depends on grain size and composition. Local myths name such places as gates, and on windy evenings the earth does seem to breathe in a voice of sand. Old chronicles describe strange things in the sky. The safest path is to ask what natural phenomena could have produced similar impressions. Sundogs and halos from ice crystals, great comets with streaming tails, auroral storms at lower latitudes than usual, volcanic sunsets that burn like a painted theatre. Our ancestors observed carefully. Translating their metaphors into modern physics is part art, part humility. Navigators sometimes report instruments that wander. The list of culprits is long. Local magnetic anomalies from iron-rich rocks, ionization layers in the upper atmosphere that bend radio waves and make a beacon seem to slide. Oceanic eddies that carry a ship off a track while the water around looks still. In rare cases, false echoes and ghost images confuse modern sensors. The ocean and the sky are both restless, and devices are replacing experience only slowly. A lava lake looks like a cauldron of myth, but it breathes with a surprisingly regular pulse. Gas bubbles rise from deep magma, pressure builds under a crust. Then a fountain opens and the lake overflows. The cycle repeats. Changes in gas composition, chamber geometry, and inlet rates shift the tempo. Because the plumbing is hidden, we watch the surface like a physician reading the beating of a heart and infer what pipes and chambers must lie below. These questions range like constellations across our shared sky. Some will be answered by a single clever experiment, others by observations that take decades to accumulate, and some may remain open simply because they ask for a kind of understanding that goes beyond mechanism into meaning. For now, they are good company. They let the mind drift along quiet coasts of ignorance and listen to the tide that is knowledge rising a finger width at a time.